Hello, everybody. My name is Wuji Wang. I'm a PhD student at Heidelberg University. My supervisor is Domenico Vitalik. We also closely collaborate with Joel Bernay and Carlos de Brick at ESO. Today, I'm very glad to share with you at this conference our recent work. Is based on a paper we published last year. The title of my talk is Spatially Mapping the Metal-enriched Absorbing Circumgalactic Medium of a Massive Galaxy at Redshift 4.5. Okay, let's start. The general topic of my talk today is about the galaxy evolution and feedback. In the theory of galaxy evolution, the central galaxy will create gas from the surrounding medium to support, apply its star formation activities, and also the galaxy will eject the gas through agent outflows or jet into the surrounding medium. And this feedback is a very key component in regulating the galaxy formations to and the evolutions to shape the galaxies into the way we observe it at the present. And the type of object we are interested in to study the feedback processes is high-redshift radio galaxies. The high-redshift radio galaxies are basically the type 2 quasars. So with of course, with a very powerful jet, as the images show here, example given here, some of the radio jet can be as extended as several hundred kiloparsec, so really into the circumgalactic medium, showing the jet gas interaction. And the high redshift radio galaxies are hosted by some of the most massive galaxies at any given redshift. So basically their stellar mass are very high, like 10 to the 11 or 10 to the 12 solar mass. And they already established such a high stellar mass at a very early time of the universe. For example, like a redshift 3. So they are really the monsters in the early universe. And the high redshift radio galaxies is basically only the only type of object in which we can study the quasar mode feedback, the radio mode feedback, and the host galaxies all together. So make them very unique laboratory in our work. So we have a sample of MUSE observations of high redshift radio galaxies, 8 of them. And the movie show here are the MUSE observations. And the movie are looking around over the rest frame Lyman-alpha emission of all of our sample target. The redshift is labeled here. As you can see, the most prominent feature of the Lyman-alpha emission halo is they're very extended. And some of them are extended like over 100 kiloparsec. So really showing a bridge between the interstellar medium to the outskirt circumgalactic medium. And when the image looking around, you will see that the Lyman-alpha emission halo gets dimmed at some point. That is due to the neutral hydrogen or the H1 absorptions. And there are other features is worth to mention here is there we often observe some of the metal elements like through the carbon-4 and the nitrogen-5. So that maybe give us a hint that these giant Cassian halos have a origin from the inner of the galaxies. And that's why it's probably trace the feedback processes and why we're interested in study this type of object through the MUSE observations. And next, we are going to talk about the work we, based on the paper we published last year. So in this paper, we focused on one target, namely the 4CO 4.11 at redshift 4.5, so our highest redshift target. So in this pilot study, we explore the ability of MUSE to spatially map the emission halo of this radio galaxy. And I listed our collaborators in this work here. On the right-hand side image, we show the narrowband Lyman-alpha emission halo. So giving you an idea how extended the object towards the Lyman-alpha halo of this radio galaxy be like 70 kiloparsec, and overlaid in the green, I show the radio jet contour. So give you a comparison. What is the scale compared between the radio jet and the Lyman-alpha emission halo? And on the left, the spectrum is extracted from the 1 arcsecond aperture, whereas the UV spectrum of our emission halo. And I marked in red the prominent UV lines to give you to show the prominent UV emission line we're going to focus in this work. And the first emission line we focusing on is, of course, the brightest Lyman-alpha emission line. And the spectrum is a zoom in Lyman-alpha line you see here. And you can see there is a lot of the Lyman-alpha line suffered a lot from the absorptions, namely the H1 absorptions. So to describe or fit this line, well, we need to take care of the intrinsic emission, which we use the Gaussian model, and the absorptions, which we use the Voigtgate profile. And the best fit is given in the dark matter line here. And from this fit, we can get the column density. So how much of the neutral hydrogen is there? And from that, we can construct the intrinsic emission, which given in the olive line here. And this is only 1D spectrum extracted from a circular aperture, but with MUSE, you can do more, of course. But first, there is a step I want to stress that is the spectral resolution of MUSE is not very high. So that's why we propose to use the UVs to observe the Lyman-alpha emission halo of 4 of our sample target. And we get our proposal is approved, and we are in the phase of collecting the data. And we are really excited to see how the data will tell us. So why we need the UVs observations, I give you an example here, because the MUSE spectral resolution of MUSE is not high enough. There is some narrow absorbers could be missed due to the MUSE spectrum. For example, the MUSE spectrum you see in the top panel, it didn't give us a resolved narrow absorbers, but in UVs, the narrow absorbers is very clear here. So that's maybe have some degeneracy when we just look at the MUSE spectrum. So that's why we need the UVs. Again, back to the MUSE. With MUSE observations, we can always do more because MUSE is an IFU instrument, so we can get the spatial information simultaneously with the spectrum information. So next step is to spatially map the Lyman-alpha emission halo of our radio galaxy. And to do that, the first step is to spatially bin the cube, the data cube of MUSE, and to increase the signal noise ratio to give us some better fit. And the tessellation map I show on the left-hand side is we bin our data into 64 binning regions, which means there are 64 Lyman-alpha spectrum we need to fit. And we fit following the fitting procedures I showed you just previously in the single Lyman-alpha emission line. We fit it similarly 64 times. And from that, we can construct not the observed emission, but the intrinsic one, the absorption corrected one. And the map I show here is an intrinsic emission mapping of the Lyman-alpha result. So on the left-hand side, it's a Lyman-alpha surface brightness map, and it's an intrinsic one, so nicely centered around the radio core, basically the radio galaxy, host galaxy. And on the right-hand side, we have the WAT map, which is a non-parametric line width measurement. So giving you how perturbed the line emission is, and it has some higher value in the southern part, which coincidentally with the approaching radio jet, so maybe some hint of the jet gas interaction there. And the most interesting result of the spatial mapping come from the mapping the column density of the first absorber. Just a reminder, the first absorber is the absorber around red velocity 0, is the absorber here. So we map the spatially its column density, and we identify a column density gradient from the southwest here to the northeast there. And it's not alongside the radio jet, but for this absorber, besides the column density, we also identify a velocity gradient. The velocity gradient showing on the right-hand side is nicely alongside with the radio jet, so that could be some evidence the jet is have some relation with this velocity, so it could be traced. The velocity gradient could be traced by the radio jet. And I show here some examples to give you an idea how the individual fit looks like. So basically, there are all outskirt fittings, so the low signal noise regions, but the fit looks quite satisfied. Okay, that's previously all about the Lyman-alpha, but as I mentioned, we often observe there are some metal elements in the emission halos. So for these radio galaxies, we also observe the carbon-4 and nitrogen-5 lines. But for the observer 1, we also identify is in the absorptions in the carbon-4 and nitrogen-5. And I just leave the details here for fitting the lines. Basically, we use a similar procedure using the emission profile on top of the class C void gate profile to describe the line. And we constrain the column density of the metal absorbers. And because we have 2 lines here, so we can constrain its metallicity. And for now, we have the column density of the observer 1 of the neutral hydrogen, and it's a spatial gradient we see. And we also constrain the metallicity of this absorber. So there is where we come up with this outflow shell model to describe the observations we see. It's a simple toy model to explain the observations we have, but it can, in some extent, explain what we observe. And I just explain simply here how the model is going to work. In this sketch, the dark green annulus showing the observer 1 is based on our theory, it could be ejected previously in the star formation activities of the host galaxy or due to the AGN activities. And then when the observer 1, basically the Gaussian shell is ejected, the radio jet is launched, and the radio jet is catching up and interact with these absorbers. So, and then the column density of the observer 1 we see is due to a geometric effect in the north, where the column density is higher. Our line of sight observers line of sight interact the most with the medium, and causing its column density is high there in the north, and it keeps decreasing due to the geometric effect we show here in this sketch. And in the south, it keeps decreasing because the south jet is the approaching one. It could probably catching up with this ejected Gaussian shell and causing the column density to be disturbed and lower in the south. And this is a very simple model, but it could explain our observations, and through this analyze and observations, we are seeing the enrichment and redistribution of metals of very early galaxies in the universe. We see the distribution of metals in this circumgalactic medium, probably. Okay, that's all of the work I'm going to share about this pilot study. And if you remember, we have 8 high-redshift radio galaxies of our MUSE sample. So the next step is to do the similar trick to map the Lyman-alpha emission halo on probably even the metal halos, the metal emission lines, spatially mapping them to get a statistical sample could probably do some interesting analysis there. Okay, that's all of our MUSE observations I'm gonna say today, but we are really excited, and because we have one proposal approved of the JWST cycle 1 observations. So basically, we are going to use the near-infrared spectroscopy IFU on board of JWST to observe 4 of our MUSE sample targets. So the JWST, again, I just showing an example here. The field of view of JWST is smaller, but its spatial resolution is higher. So that gives us ability to really zoom into the center of the host galaxies to see how the feedback processes is built up from the center and combined with our MUSE observations, the outskirt in the circumconducting part, to show how the feedback is built up from the center to the outskirt. And as you all know, that JWST is successfully launched and successfully being commissioning in the meantime. So let's hope we will get the data soon, hopefully later this year. Okay, that's all I want to show today. So just a basically brief summary here. The pilot study of the 404.11, the spatial mapping of it shows that we're seeing the enrichment and redistribution of metals in and of the circumconducting medium driven by a very powerful AGN in a very massive galaxies near the cosmic noon. And the next step is to do the similar trick to analyze the whole MUSE sample. And after that, we probably gonna compare our result of the Lyman-alpha emission halo to some other type of AGNs in the early universe, because you know the Lyman-alpha emission halo is a universal feature kind of to the galaxies in the early universe. So we're gonna see if there are some, we're gonna do some comparisons there. And of course, JWST data will give us some zoom in view of the jet gas interaction and how, and probably the information of the host galaxy to see how the feedback is built up and how the jet and the gas is interact for our high-redshift radio galaxies. And with that, I'm going to thank you for all of your attention. And if you're interested in our work or have any questions, please contact me. Okay, thank you very much.